Hi, all. We're going to walk through the system analysis for our bungee jumper. Now, we do a system analysis so that we can take this really big, complicated problem and break it down into smaller pieces. And then we can look at each piece by itself, and it makes our problem easier to navigate through. So we're going to build this system analysis together for our bungee jump, and then we will use it as a map to get all the pieces of information that we need to get us to the bungee jump. And remember, we want our bungee jumper to have fun and also be safe. So that's the whole point of it. So let's take a look at what we already know. So I'm going to start us on the energy bar charts, since that is something that we did recently. Remember, when our jumper is at the top of the jump, ready to go down, that jumper has a lot of potential energy. It has a really big height, but it's not moving yet, no velocity. So since gravitational energy is mass times gravity times height, the jumper has height, so the jumper has gravitational energy. So let's redraw this bar here to show that our jumper has gravitational energy. And then our jumper kinetic energy is going to be 1/2 mv squared. And since our jumper has no movement right now, no speed, no velocity, our jumper also has no kinetic energy. Elastic energy is stored in the stretch. The more stretch the cord has, the more elastic energy that cord will have. So for now, that's all we know. It's going to be related to the stretch of the cord. And since at the beginning, our cord's not stretched at all, our jumper has no elastic energy, or our cord has no elastic energy. So our total energy in this case is all gravitational energy. It's completely made up of gravitational energy. So energy total equals energy gravitational. And then if we scroll down and look at our jumper at the end, our jumper still has some height, so it's still going to have some gravitational energy, but it doesn't have a lot of height, so it's not going to have a lot of gravitational energy. Our jumper also jumped off, flew through the air, and then got slowed down by that cord. And at the end, our jumper has stopped. So at the end, our jumper also has no kinetic energy. So we'll put a little line there to show that it's a 0. Our cord, however, is stretched as much as it possibly can be stretched. And so all of that potential energy that was lost is actually transferred into elastic energy. So our total energy here is going to be elastic energy plus gravitational energy. I'll write that down. Energy total equals the little bit of gravitational we still have, no kinetic energy, and the elastic energy that we now have stored in that rubber band that has stretched. Okay, so take a minute and write down these bar charts, write down these equations. We're going to use these as we walk through our system analysis. Pause the video if you need to get all of this written down. Now, I want to go through this system analysis and talk about the information we have at the very beginning. Remember, this information we have at the very beginning that we can measure, these are called inputs. So anything that's an input, I'm going to write in green. And once we build our app for the amusement park to use, and different riders walk up to the app, These are the things that the amusement park can change. So we'll highlight these in green, and that way we'll know these are the things we can change on our spreadsheet. So massive jumper is one of those. It's going to be an input. It's going to be something we measure. Measure jumper's mass. For our simulation, we're just going to measure the mass of whatever we drop, the Barbie or the water bottle. Starting height is another input that can possibly change if we throw the bungee jumper off of a stairway or a balcony. So starting height is something we can just go measure the height of whatever we throw our jumper off of. And this is going to be an input. So I'm going to put measure height right there. We'll just go measure it. Okay, how much string are we going to use? We don't know this. Actually, this is going to be our end calculation. This is the big thing that we're going to figure out in the very end. So I'm going to box it or highlight it in red so that I know I don't know this yet. And this is going to be my final calculation. All right, length of unstretched cord. So how much elastic cord am I going to need to attach to my jumper? I don't know that yet. That's something we're going to have to figure out. So it is going to be something we calculate. Let's box it in orange or highlight it in yellow. And this is something we're going to find. We're going to find by the end of the lab. Oh, shoot. I take that back. We're not going to measure it. We're not going to calculate it. Let me erase that real fast. This is just a decision we're going to make. This is an input. We can change it if we want to, but actually I think we're just going to all use 0.5 meters for this jump that we do together. So this is actually an input. Easy. One more thing we already know. Great. Okay, spring constant. So this is the strength of our spring or of our elastic cord. Now, this is something we can find out. Looking at this elastic cord, I don't know what the strength of it is, but we can find this. So we're going to do this in a mini lab where we look at force versus the length of the stretch. So this will be something that we're going to spend some time on looking at and trying to find. So we can know this is a calculation. All right, moving down. Distance the cord stretch. So when I drop my jumper off on the super fun bungee experiment, how far is this cord going to stretch during the jump? Okay, also something I don't know yet. This is also something that we can calculate. So we're going to spend some time on this, in a lab. That should say LAB. And this lab is going to be elastic energy versus the length or the distance of the stretch. All right, the next thing we have to know is the height of our jumper. And this, again, is something we're going to just have to measure the jumpers as they come up to the amusement park ride. This is something we can measure. We can measure the height of our Barbie or our water bottle. So this is an input for us. And then the ending height is actually going to be something that we decide together. So this also can change. Again, we want the jump to be fun, but also safe. So we have a buffer region, and then we also have like a no, this is dangerous region. And we're just going to say for now that that's going to be 1 meter, just so we have an input. And then as we go, decide whether we're going to throw the Barbies in the water bottles off of the balcony or a staircase. We can figure out what that height should be. Okay, so now we have a plan. We can go and measure all of our green inputs. We can go and find the calculations we need to do and the math models we need to do. And then we can have this final calculation. So one note on our distance, the cord stretched lab, this is going to be elastic energy versus length of our stretch. Now, elastic energy, we have talked about how this is the energy stored in the cord as it stretches. But how do we actually get this? And actually, our bar charts will help us get this. Notice that elastic energy here is related to the gravitational potential energy and the total energy. So gravitational energy, we can just calculate. It's mass times the strength of gravity in the Earth, or 9.8, times the height. So we just plug in our mass, we plug in our ending height, and we have our gravitational energy. Our total energy comes from the top. Remember, at the very beginning, before our jumper has jumped, our total energy was all gravitational energy. So we can actually use our gravitational energy from the top as our total energy. So let me go back down. Again, this is going to be gravitational energy at the beginning, at the start, which is mass times the strength of gravity times the height at the start. Whereas this is height at the end. So elastic energy can be calculated in this way for our lab. And then once we have that, and we have the strength of our spring from our mini lab, we can address this final calculation. So in this final calculation, what we want is the length of the string. But in order to get the length of the string, it's actually only the length of part of our jump, right? So our starting height, our height in the beginning, which is up here in green. Remember, we're going to measure the balcony that we throw the jumpers off of. That's equal to everything below it. So that is equal to the length of our string plus the length of our elastic cord. I'm going to put L cord plus the length of our stretch. How far, so the cord plus how far the cord stretches, plus the height of the jumper, plus the height at the end. So by the end of the lab, we should know all of this. We should have measured the starting height. We know the cord is going to be 0.5 meters. We're going to figure out how far it stretches. We're going to measure the height of our jumper. We're going to have the height at our end. And then we can use all that to find length of our string that we need for this Barbie to have a fun and thrilling jump. And then we have all of our pieces. So let's go ahead and solve this equation for length of the string. It's going to be height at the start minus everything else, minus length of the cord, minus length of the stretch, minus height of the jumper, minus height at the end. Okay, so we have a game plan now. This is a very complicated problem, but we've used our system analysis to break it into pieces, and we can tackle these pieces one at a time to figure out how to help this jumper have a fun and safe jump. Here we go.